Okay, lecture 68. Kepler's second law. So we're going to talk about Kepler's second law in more detail, and we will demonstrate it a couple of ways. The first way we'll demonstrate it is using the angular momentum, the concepts from angular momentum that we talked about last week. In the second way, we'll do it the way that Newton did it. Okay, it's a more of a geometrical approach. So what I've drawn here is an elliptical orbit, where maybe this little dot here could be Earth. At the focus of the ellipse, at one of the focuses, at one of the foci, we have the Sun. And you kind of see what's going on here. So we have the Earth that's going in this direction. Right? So I've drawn a little velocity vector here. And of course the magnitude of that vector times some delta t will propel it forward to this new time here. Yes?
Yeah.
We have to imagine that, this is I drew it exaggeratedly large, right? We're really considering really tiny delta t's, so this would be, more like down here in reality. So I've exaggerated this area that I'm describing here. So we're looking for the area here, this area that I've outlined. And you can see that it's going to be half the area of this parallelogram that is constructed by r and v delta t. All right? And the basis of what we're going to do here, let me remind you, conservation of linear momentum, right?
Yeah.
So we have that the sum of the forces is equal to mass times acceleration, which is mass times delta v over delta t, right? Yeah. We can think of m delta v as kind of a delta p over delta t, right? If there are no forces acting on the system, right, then linear momentum is conserved. So that means that this is equal to 0. Yes? That's not saying that there are no forces between the objects that make up the system. I'm saying the external forces, things outside the system. So if that's the case, delta t is equal to 0, which means that delta p is equal to 0. And delta p is just, p final minus p initial equals 0, which means that p final is equal to p initial, or that the momentum, the total momentum, is constant. That's for linear momentum. Similarly, if we change forces to torques, you'll recall, let me just get rid of all that. If the sum of the torques is equal to 0, right, then that means that delta L, the change in angular momentum, is equal to 0, which means that the angular momentum is a constant, right?
Yeah.
Angular momentum after is equal to angular momentum before, if the sum of the torques is equal to 0. So in this system, which includes the Sun and the Earth, that's part of the system, I'm assuming there are no external forces and no external torques. Okay?
Okay.
If that's the case, then we're going in with the assumption that the angular momentum, L, is constant. So in the time delta t, the planet moves v delta t, right? The velocity times the time interval, yes?
Yeah.
So the area, right, we're looking at the area of this parallelogram, right? The area is equal to 1/2, because it's only half this parallelogram, yes?
Yeah.
1/2 r cross v delta t. Okay?
All right.
So r cross v delta t, that's the area of this parallelogram. Okay?
Yeah.
Half of that is the area swept out in this time period delta t by the planet. Okay?
Okay.
If I introduce mass into this, right, then I can rewrite this as 1/2 r times m v delta t, but I've got to divide out an r here, so an m here. Since I put an m in here, I've got to take it out over here. 1/2m, yes?
Yeah.
Mass times velocity is just momentum, right?
Yeah.
So that's 1/2m r cross p delta t, and I think we are pretty much there. Of course, we want the magnitude of this, right? So let me put magnitudes around all of these things. We're not interested in the vector aspect of it. Remember, the vector will be outwardly pointed, I think. Let's see, r into vs, out of the board. But we're not interested in that. We're just interested in the magnitude. That's the number that corresponds to this area, okay? Almost there. But what is r cross p? We can pull this delta t out, right? And I can put that over here, I suppose. Delta t, right? And I'm left with just this, r cross p. P, of course, is because v is a vector, p is a vector, right? That's the linear momentum vector. And remember that L is defined as R cross P. So that means that this is equal to delta T over 2m times the vector L, the magnitude of it anyways, right? So what can I write in the end? I can write that a change in the area is equal to 1 over 2m, and I'll divide the delta T over here, you see?
Yeah.
So that says that the change in area per change in time is a constant, right? Because this is a constant. So this is essentially a proof of the equal area in equal time. Okay? Because if delta A over delta T is constant, then it doesn't matter whether I'm talking about this piece of area swept out over here, or, let me draw it in a different color. Or this area swept out over here, right? It's a constant because the angular momentum is a constant. Okay?
All right.
So that is how you would prove this using angular momentum and the ideas that we developed last week when we talked about angular momentum.